Hello everyone, my name is Kang Qiao from Nanyang Technological University, School of Computer Science and Engineering. Today, I want to introduce you to our paper and work on steering quadruped animal agents with reinforcement learning. Traditionally, body rehabilitation is a long-term process which mostly involves a set of physical equipment and also assistance from professional medical staffs. For patients, this is a repetitive process that is often very inconvenient and boring. Fortunately, the development of VR has provided a brand new platform for users to interact with computers. The patients can now immerse themselves into a computer-generated 3D environment during their rehabilitation process by just having a set of VR equipment in their home. Therefore, based on these thoughts, we have developed a VR hunting game as shown in this figure. The player can move freely around a forest environment with all kinds of different animals such as bears, wolves, deer, etc., and is able to control a virtual bow which has unlimited arrows for him to shoot down these animals. Our objective is to generate in-game intelligent animal non-player characters with high level of autonomy to minimize users' uncomfortableness and maximize their experience while gaming. An integrated motion behavior system of an intelligent NPC agent consists of 4 major layers. Our key innovations in this paper can be embodied from the steering layer and the locomotion layer. First of all, I want to introduce you our proposed constraint steering model. To represent the rig of the animal, we took an approach that strictly follows the basic laws of kinematics and mechanics to determine the motion and path of the animal character. Any physical object with mass must have a non-zero radius, thus possesses a moment of inertia, shape of a rigid body that can decently represent the rig of most terrestrial animals such as wolf, bear, deer, etc., is an ellipsoid, as shown in this figure. By idealizing these animal rigs as ellipsoid-shaped rigid bodies, we can easily steer them around the environment by just providing them a steering torque and a steering force as inputs. Besides displacement and angular displacement, which are derived as final outputs, we are also able to access and tune important variables during this derivation such as acceleration, angular acceleration, velocity, angular velocity, mass, and moment of inertia. Specific constraints can be applied on these variables for different types of animal to generate a set of diverse motion behaviors. So here I know you may want to ask about how this so-called steering force and torque is computed. I have recently written another paper concerning the navigation layer based on this constraint steering model, in which we explained in details all the related algorithms and achieved full autonomy steering force update based on the current motion parameters of the character and its given task, such as hover, pursuit, flee, obstacle avoidance, etc. If you are interested in this paper, feel free to email me afterwards. By applying our constraint steering model with some predefined animations, we can already witness these animals autonomously navigate themselves around the forest. However, the biggest disadvantage of script motion is also very obvious. That is the foot sliding issues. Therefore, we have created our own animal skeletons, as illustrated in this figure, where a wolf character is used to represent a generic quadruped IK model. It can easily be extended to other types of animal characters. The wolf skeleton consists of a total number of 14 bones and 20 joints, with each of these 20 joints specifically named and constrained. Some important joints include one root joint that keeps track of the position and orientation of the model and determines the position of the 5 subroot joints of the body. 9 joints which serve as possible end effectors, respectively located at the 4 subroot joints above the upper legs, 4 joints on the feet, and last but not least, the head joint. In this paper, we will look at a typical case scenario, that is, training of a predator agent whose objective is to catch up its prey target as fast as possible while keeping its balance and correct limb movements by a total number of 39 continuous actions corresponding to the rotation and strength of each joint. The basic agent observations include root velocity vectors of itself and the target, collision detections between its body mesh and the ground. In addition, the limbs should properly take turns in performing the swing and stance phases for different behaviors. When the agent is walking, if the limbs of one side is under swing phase, the limbs of other side must be under stance phase. For running, this is similar. When the front limbs are under swing phase, the hind limbs are required to stay on the ground and vice versa. These IK constraints are implemented by adding collision detection between the foot mesh and the ground into agent observation and punishment for misconduct into the reward function. PPO is used as one of the main learning algorithms in this experiment for its simplicity and robustness. The behavior of the prey target is another critical factor that influences training of the predator agent. Some vanilla configurations may be simply generating a new stationary target or position translation toward the opposite direction of the agent at the beginning of a new episode. Instead of staying on its position and wait for the predator agent to reach it, autonomous steering target will first perform collision detection against a pursuit agent within its detection radius. If the pursuit agent is not detected, it proceeds to execute the hover behavior, otherwise execute the flee behavior. In both hover and flee, the target agent will always be constrained by collision avoidance force to keep itself from getting cornered. After 15 million steps of training with PPO and soft actor critic, cumulative reward of both algorithms, training with autonomous steering target reached to around 2,200, which surpassed the benchmark reward of 2,000 training with vanilla dynamic target. 2 timers recording the episode length for both agents are set based on a total number of 100 episodes. Our quadruped IK agent outperforms the vanilla agent by approximately 25% in an arbitrary environment. Major technical contributions of this study are made to inverse kinematics embedded motion control, quadruped locomotion behavior adaptation, and dynamic environment-informed reinforcement learning. Instead of designing specific dynamics algorithms, PPO learning scheme is combined with the autonomous steering target for a more challenging training environment. Such an autonomous steering target enables a variety of different behaviors. In fact, the same approach can also be used to train intelligent fleeing agent and much more. This is the end of my presentation. Thank you everyone for your attention.